Hi, and welcome to the second video of two videos for section 7.1. In this section, we're now going to be proving trig equations. So in the first video, we were just simplifying, proving similar idea, but it actually is a little bit easier for us because with the simplification, we didn't know what the answer was supposed to be. So we kind of just had to hope that as we were exchanging things and canceling things out, that we got to where we were supposed to go. With the proofs, both sides should be equal to each other. That's what we're trying to prove. So we know what we're trying to get to on one side as we simplify it. So for proving trig identities, or let's call them trig equations, we're going to follow the three steps. First, we're going to start with one side. And it's usually the more complicated side. So I know what you're saying. It's like, well, if I can start with either one, why would I want the complicated one? The reason being is it's a lot easier, like our expression goes, go complicated. We want to make complicated things simple. So if we start with one side that's real simple, and we try to make it super messy to get to the other side, that's going to be a lot more difficult on us than choosing something that may look complicated, but will simplify to something very nice and easy for us. So we usually want to go with the more complicated side. The second one is we're going to use known identities. So that's what we had at the start of video 1 for 7.1. We're going to use our known identities to simplify the expressions and three, and this is not necessarily a step, it's maybe more of a suggestion, is we want to convert to sine or cosine if appropriate. So again, a lot of times it'll make it easier on us if we switch to the sine or cosine functions. That way, if all we're dealing with in the problem is sine and cosine, stuff will tend to cancel out for us. So let's look at a few examples. So I'm going to erase this just so I got the whole board space here to work the examples. So if you're still catching up on the writing, go ahead and pause and then come on back. All right, so example 1 says the following. We want to prove that cosine of theta times secant of theta minus cosine of theta equals sine squared of theta. As the step suggested, we're only going to work with one side because if we start converting both sides, we may never get it to match up that the left side equals the right side. And ultimately, that's what we want in here, is that when we get to the very last line, both sides are the same. Now, here's where I'll caution you. On the exams, on the final exam, we know that what? If we start working this left side, at some point it has to get to sine squared. But you don't get to use magic math. You don't get to say at some point like, well, I'm stuck, so I'm just going to say that this whole thing equals sine squared because I know that's what the right side should equal, and now I'm done. If you do that, you're not going to get credit for it. You have to show a continuity of your work, how you get from one line to the next. All right, so what was our step 3, or our suggestion in point 3 was to change things out to sine or cosine. So the only one we have here is this guy. So I'm going to do that first. Cosine of theta is equal to what? Well, secant is 1 over cosine of theta, and then minus cosine of theta. And I'm not going to worry about the right side. Just going to bring that guy down because hopefully at the end I get the left side says sine squared of theta. So I'm not going to worry about the right side even at this point. I'm only working with the left side. Now I've converted it, so now I want to distribute. So I have the outside minus these two terms. So cosine theta times the first, cosine of theta times the second. So cosine of theta times 1 over cosine of theta, what happens? The cosines cancel out, and I just get 1. Now for the second term, so I have this minus sign in here. So cosine of theta times cosine of theta is equal to what? It's cosine squared of theta. What does this guy look like? That's right, our holy grail of our Pythagorean identities. So this thing is equal to what? This is equal to sine squared of theta, which happens to be equal to the right side, sine squared of theta. And a little mathematical notation, we'll put a pound sign or hashtag, I guess you guys might know it as, when we're done with the proof. So the left side we showed is equal to sine squared of theta, which is what the right side is as well. So this one's not too bad. Again, just following the idea. Pick one side, normally the more complicated, that's this one. Change out the cosine or sine if we need to, and then use our identities to simplify. All right, let's look at another example. So we want to prove that 2 tangent of x secant of x is equal to 1 over 1 minus sine of x minus 1 over 1 plus sine of x. So first off, what's our most complicated side? I would say probably the right? We have two terms, we have fractions, we have different denominators. So this is where I'll give you guys sort of a heads up, is that as you're trying to do these proofs, when you end up with something like this, where you have two terms and they have different denominators, almost always you're going to need to find the LCD and combine both terms. I would say 99% of the time that's the way to prove these. So in this case, what would our least common denominator be? Well, the least common denominator is going to be what? 1 minus sine of x times 1 plus sine of x. So think of it instead as like fractions. If I had 1 over 3 minus 1 over 4, well, what's my LCD? It's just 3 times 4, or 12. So in this case, it's just 1 minus sine of x times 1 plus sine of x. So if that's our LCD, and we want to convert both of these terms on the right to have that as the denominator, for the first one, 1 over 1 minus sine of x, what do I need to multiply this one by in order to get the same denominator? Well, I would have to multiply the denominator by 1 plus sine of x, which means I have to do the same thing in the numerator. So that what I'm really multiplying by is 1. I'm just going to change the way that it looks. And for the second term, same idea. I have 1 over 1 plus sine of x. If I want to have a denominator as 1 minus sine of x, 1 plus sine of x, I need to multiply numerator and denominator by 1 minus sine of x. So now let's work with each of these terms. So this one here, because I'm multiplying, what do? I multiply numerators, I multiply denominators. So I get 1 times 1 plus sine of x. So that's what I end up with in the numerator. And in the denominator, I'm going to multiply these two together. And what happens? Well, if we do FOIL, I get 1 times 1 is 1, plus sine of x minus sine of x. So the O and the I, the outside and the inside terms, cancel. And I get minus, because negative times positive is negative, sine squared. And what does this guy look like? That's right, one of our main Pythagorean identities. Now let's move to this second one. Multiply these two together. So in the numerator, I get 1 minus sine of x. And because these guys are the same, as this first term, I get the same denominator. That's ideally what I want, because I want to be able to combine these two. So if I don't have the same denominator, I've goofed something up. So now, this guy is equal to what? This is equal to cosine squared of x, just like this one. So this is really like 1 plus sine of x over cosine squared of x minus 1 minus sine of x over cosine squared of x. So now, because they have the same denominator, let me bring this up over here. When I subtract them, I will still have cosine squared of x in the denominator. But here's what I would suggest you. Put parentheses around the numerators, because with this minus sign, that's more often than not going to cause trouble for people. So we have what? We have 1 minus 1, which is what? 0. And then sine of x minus a negative sine of x. So that's what? Sine of x plus sine of x, which is what? 2 sine of x. So again, essentially all I'm doing is distributing this negative sign. So the second piece becomes minus 1 and plus sine of x. So when I combine the numerators, 1 minus 1 is 0, it's gone. Sine of x plus sine of x is 2 sine of x. So now here's another little trick you're going to be able to use in proofs. So cosine squared of x is essentially what? Cosine times cosine. So what I want to do is break this thing up. 2 times sine of x all over cosine x times cosine x. And so really we can leave like a 1 out over here, right? And why would I do that? Well, what are we trying to get to eventually? We're trying to get to prove that this thing is equal to 2 tangent of x secant of x. So if I look at this as 3 parts, what do I get? 2 over 1 is 2. Sine of x over cosine x is what? It's tangent of x. And 1 over cosine of x is equal to what? Secant of x. Which is the same thing we started with on the left, which means we are done with that proof. So we've shown that the left side is equivalent to the right side. So again, I'm going to go ahead and erase this. If you guys are catching up or following back, go ahead and pause, and I'll see you on the next example. All right, so the last example we're going to do, here's another proof. We want to prove that cosine of u over 1 minus sine of u is equal to secant of u plus tangent of u. So here we are. Step 1, we want to decide what's the most complicated side. Again, I would say probably the left because it has a fraction. Here's another tip. So I've given you a few. When you have 2 terms, find the LCD, combine them. If you have a cosine squared, see if you can split them up and separate the pieces. The last one is this kind of problem, where you have just one fraction. If we want to simplify this, we're going to use what's called the conjugate. So if I have x plus y, the conjugate is just x minus y. So we did this when we were like rationalizing equations or rationalizing expressions. So if I have like 1 plus the square root of 3 and I want to rationalize the denominator, I would multiply it by 1 minus the square root of 3. That way, like we just saw in the last problem, when we FOIL it, what happens? The middle terms, which would have the square root, would disappear. So what we're going to do on this left side is multiply the top and the bottom. So we're going to start with cosine of u over 1 minus sine of u. If I multiply this by the conjugate of the denominator, so top and bottom, by what? Well, 1 minus sine of u, the conjugate would be 1 plus the sine of u. Again, just like we last saw just like we saw in the last problem, what's going to happen? The sine terms will disappear. We'll get a sine square, which gives us what? Our, holy grail Pythagorean identity. So again, I want to multiply the same on the top and the bottom. So if I do that, what do I get? I get on the top cosine of u times 1 plus sine of u. And in the denominator, what do I get? Well, I get 1 times 1 is 1, plus sine of u minus sine of u. They disappear again. That's the reason we're doing this. And then minus sine squared of u. Now you could distribute the top, but I'll show you why you don't want to yet. Because what? This bottom is going to convert to our cosine squared, so one of these guys will cancel and it'll simplify our work a little bit. So I get what on the numerator? Cosine of u and 1 plus sine of u all over 1 minus sine squared. That's equal to what? Cosine square of u. So this guy is really like what? This is really like cosine of u times cosine of u. So this 1 in the numerator cancels with 1 in the denominator. So I'm left with what here? 1 plus sine of u over cosine of u. So now I have a fraction. And as long as I have just one piece in the denominator, I can separate the both over that piece, right? So 1 over cosine of u plus sine of u over cosine of u. 1 over cosine of u is what? That's secant of u. Sine over cosine is what? That's tangent of u. What am I trying to prove? I'm trying to prove that it's equal to secant of u plus tangent of u. So again, we are done with that proof. So a few different examples, but the examples that highlight the tricks you're going to want to use. Change out to sine and cosine if you can. Find common denominators if you have two terms so that you can combine them into one. And if you have just one term with a fraction, multiply top and bottom by the conjugate of the denominator, and that'll generally produce one of our trig identities, which you can use to simplify to get to where you're going. So that's the end of video 2 for section 7.1. We'll see you in section 7.2.